Okay, so let's solve another example. And in this example, we will consider the second part of the problem too in our midterm. And let's try to solve the question with the Routh-Hurwitz method. You don't have to use the Routh-Hurwitz method for that question, but let's try to do that as an exercise, okay? So let me write example. So let D of S be a characteristic polynomial of a system. Okay. And D of S is equal to S cubed plus alpha times S squared plus alpha minus 1S plus K plus alpha. Okay. And assume that we observe sustained oscillations in the step response of the system when K is equal to 3 alpha. Okay. So in step response, we observe sustained oscillations when K is equal to 3 alpha, where K and alpha are positive real numbers. Okay. And we would like to find K, alpha, and poles of the system. And K is equal to 3 alpha. All right, so since this is a characteristic polynomial of a system, it means that it is the denominator of the closed loop transfer function. And the roots of that equation gives me the pole locations. And it says that we observe sustained oscillation. So in the step response when K is equal to 3 alpha. So you might have underdamped response where you have decaying oscillations, or you have undamped response when you have the oscillations that don't decay in time, right? So when you have oscillations that are sustained, then you have poles on the imaginary axis, then you have purely imaginary poles. Okay, and I should see that on the Routh ray as well, because those poles will be laying radially opposite in the S-plane, okay? So I should observe a zero row in the Routh ray. So let me apply the Routh-Hurwitz method for this polynomial D of S. I will start with the S cubed term and S squared, S to the power 1, and S to the power 0. And I will write down the coefficients. The coefficient of S cubed is equal to 1. Coefficient of S term is equal to alpha minus 1. Coefficient of S squared is equal to alpha. And coefficient of the S to the power 0 term is K plus alpha. Okay. So if you would like to, you can fill in zeros over there. And I will continue with the next row. Okay. And that term is, for example, alpha times 0 minus 1 times 0 divided by alpha is equal to 0. And let's compute this term over here. And this term will be simply equal to alpha times alpha minus 1 minus K plus alpha divided by alpha. So that is equal to alpha minus 1 minus, this is in parentheses, minus K plus alpha divided by alpha. Okay. So So when k is equal to 3 alpha, I observe sustained oscillations. So then I will have purely imaginary poles, symmetric on the imaginary axis. Then I should have a 0 row over here, right? So that term over here should be equal to 0 when k is equal to 3 alpha. So then I can solve for alpha there. If I can write here instead of k, I can write 3 alpha. And the whole thing becomes actually 4 alpha divided by alpha. So this will be simply equal to 4. And from there, I can write alpha is equal to 5. And k is equal to 3 alpha, it will be simply equal to 15. Okay, so then we will have the 0 in the Routh ray as expected, okay? So let me write it down as well. So 0 when k is equal to 3 alpha. And furthermore, I can construct the auxiliary polynomial here, P of S, okay? And try to find the pole locations of this polynomial when k is equal to 3 alpha. So the auxiliary polynomial is equal to P of S. I will construct it from the coefficients of the upper row over here. And that is equal to alpha times S squared plus K plus alpha. And if you replace alpha is equal to 5 and K is equal to 15 here, I will have 5 S squared plus 20. So I know that this P of S is a factor of D of S, okay? So now I know the two of the roots of D of S because P of S is a factor of D of S. And here we can also write those two poles are plus minus 2j, right? So S1 is equal to, let's say, plus 2j, and S2 is equal to minus 2j. So let's find the third pole by making a polynomial division. Okay, so I can write down D of S itself over here, let's say. So I can get S cubed plus alpha S squared, and alpha is equal to 5, so 5 S squared plus 4S plus K plus alpha is 15 plus 5 is equal to 20. And divided to 5S squared plus 20. Okay. And if I do that, I will write here S over 5. And I will get S cubed over here plus 4S. And if you subtract that guy, you will end up with 5S squared plus 20. And you'll have 1 here, such that the remainder will be equal to 0. So good, then I can write D of S as I found the third pole as well, which is at minus 5. So I can write D of S as 5S squared plus 20 times S over 5 plus 1. Or I can write it down as S squared plus 4 times S plus 5. So S3 is minus 5. So we found all pole locations when k is equal to 3 alpha, and also we also found the k and alpha values, which were 5 and 15. But as an exercise, let's carry on filling in the Routh array and validate our results as well. Okay, so I will continue filling in the Routh array. So if we have 0 over here, then at the end, we will replace that 0 with the coefficients of P prime of S, right? So what is P prime of S? If P of S is equal to 5S squared plus 20, and P prime of S is equal to 10. Okay, so let me write it over here. P prime of S is equal to, let's say 2 alpha S, 2 times alpha times S. So it should be simply equal to 10S. And I will replace the coefficients in the 0 row with the coefficients of P prime of S. So this will be simply equal to 10. I will do that. Sorry. So this will be 10 and 0. And if you compute the last term over here, so because of that 0 term, that K plus alpha will move here directly. So right here, K plus alpha. And now I filled in completed the whole Routh array. Now I can inspect the first column of the Routh array. By the way, K plus alpha was equal to 20, so I can write 20 as well, but it's not going to change result. And when you inspect that, as you see over there, alpha is positive, K plus alpha is positive, is 5 and 20. So there are no sign changes here. So no sign changes. Therefore, no poles with positive real parts. Okay. But the system is unstable. Say, but the system is unstable. And why? And that's because of the imaginary poles there, right? We have purely imaginary poles lying on the j omega axis. So maybe I can plot the pole positions like this on the S plane. So this is the imaginary axis, this is the real axis. And we have the pole locations as this is 2j, this is minus 2j, and this is minus 5. Okay, and because of the poles on the imaginary axis, the system is unstable. Okay.